Assalamualaikum warahmatullahi wabarakatuh. And hello, my name is Muhammad Azrif Han bin Muhammad Noor, and my friend is Shami Arif. We are from Group 6. Want to present about modeling and dynamic of asset price and Monte Carlo simulation. I will present part A, which is numerical method in finance and economic black based introduction. First, basic finance analysis, income security, modeling and dynamics of asset price. Example relate to modeling and dynamic of asset price. While part B will be presented by Shami Arif. Okay, first, basic financial asset. Financial asset can be defined as liquid asset. Example, cash, stock, bonds, and derivative. Stock are financial asset with no set ending or expiration dates. Bonds are one way that company or government finance short-term project. Derivative is an instrument or contract between two parties that derive its value from the value of underlying asset variable. The major user or derivative contract are hedgers, speculators, and arbitrageurs. Hedgers to reduce risk. Speculator to bid on the future direction market variable. Arbitrageurs is buy at low price and sell at high price. In theory, prices are consequence of an equilibrium between the supply and demand of an asset. Okay, next, income securities, basic theory of interest rates. Fixed income securities are a type of debt instrument or investment. Fixed coupon and zero coupon bonds are examples of fixed income securities. The formula can be used is formula of rate of return on investment. R equals to W1 minus W9 per W9, where W9 equal to initial wealth and W1 equal to wealth after invest 1 year. Simple interest calculate amount of interest I equal to PRT, where P total origin principal amount, R interest used at a specific rate, T for a given period. End of investment to sum the principal and original amount with interest can we use the formula WT equal W9 plus I equal W9 plus W9 RT equal W9 1 open bracket 1 plus RT close bracket. R is interest rate, T is time in years. Compound interest to accumulate the amount of interest for the next year by adding the interest of the previous years to the principal. WT equal W9 open bracket 1 plus R per M MT. Calculate the discrete compound present value. We can use the formula PV equal to sum K equal to 0 and CK per open bracket 1 plus R per M close bracket K. CK is cash flow. Continuously compound present value can be calculated. Use the formula V equal to sum I equal to 0 and CIE exponent RTI. Okay, next, modeling and dynamics of asset price. Asset price (ST) must be described as a stochastic process. Apply modeling and dynamics of asset price for more complex portfolio management models could be described or continuous time models. The multiplicative model is ST plus 1 equal to T ST y UT is bigger than 0. Additive model ST plus 1 equal UT plus ST cannot be said that ut as a non-negative value for the model price drop SST also cannot be ensured will be a non-negative value. The additive model is not reasonable compared to the multiplicative model. Natural logarithm of the stock price as log S plus 1 equal log ST plus log UT equal log ST plus ZT. Let S0 as initial price of stock and unfolding the equation of multiplicative, the equation become ST equal K equal to 0 T minus 1 UK at 0, which imply log ST equal to log S9 plus sum K equal to 0 T minus 1 ZK. By using the notation of EZT equal to V and variance ZT equal to variance square, ZT is used in computing variance. E log ST equal E log S0 plus sum K equal to 0 T minus 1 ZK. Log S9 plus sum K equal to 0 T minus 1 EZK, and the answer is log S9 plus VT. Expected value and the variance of increment in the logarithm of the stock price scala linearly with time. Variance log ST equal to variance log S9 plus sum K equal to 0 T minus 1 ZK equal to 0 plus sum K equal to 0 T minus 1 variance ZK equal to TA power of 2. In the deterministic case, the log ST equal V dt. Stochastic differential equation inform the log ST equal V dt plus variance dWt. We integrate both sides for equation in deterministic case over the interval 0t to obtain continuously compound stock price. Thus, the equation is integral 0t d log st equal v integral 0t dt. Log st minus log s0 equal v t minus 0. Log st minus log s0 equal to vt. Log st equal to vt plus log s0. And the answer st equal to s0 dot e power of vt. Therefore, this is how we obtain the continuous time model from discrete model. In the standard linear process, in discrete time, consider the following process as a building block. Wt plus 1 equal Wt plus epicenter standard deviation St, where the epicenter is a sequence of independent standard normal variable. For k bigger j, we can see Wk minus W1 equal to sum t minus 2 equal to j, k minus 1 epicenter is square root to st. Standard linear process can be defined as continuous time stochastic process characteristic by the following properties. W0 equal to 0 is actually a convention. Increment normally distribute given any time interval st. The increment Wt minus Ws is distributed as n0 t1s with expected value 0 and standard deviation square root s minus t. Increment are stationary, they do not depend on where the time interval is, but on its which. Increment are independent for t1 less t2 less than t3 less than t4, then wt2 minus wt1 and wt4 minus wt3 are independent random variable. Wt used as building block of stochastic differential equation given real constant A and B and assume that stochastic process at t satisfy the equation, we obtain the at t equal to A dt plus B dWt, where A is drift rate with measures the mean change over period T, and B is variance rate, which measures the variance change over period T. This is a generalized linear process. Second method is Ito lemma process. Ito lemma, in which Ito process as T satisfies the stochastic differential equation. Ito's lemma equation write as ds t equal to a s comma t dt plus b s comma t dwt, which is some case the continuous limit of wave epicenter n 0, 1 dst equal to a x, t dt plus b x, t epicenter t square root st. Ito lemma can be used to find a solution, at least in relatively simple case. Geometric Brownian motion assume that rates of return to be a constant value. Geometric Brownian motion can be defined by stochastic differential equation dst equal u st dt plus variance st dwt. Okay, next. Example related to modeling and dynamics of asset price. Example 1. Consider a 5-year zero coupon bond with face value 100, sold with required yield R1 equals 0.08, which is the percentage change in its price if the yield is increased immediately after purchase to R2 equal 0.09. When you using the MATLAB, P1 equal to 98.0583, while P2 equals 64.9931. So the final answer is minus 0.0450. We see that we have a 4.5% decrease in the value of the bond. Note that this loss occurs only if you have to sell the bond before maturity. No harm is done if you keep the bond no maturity, but this makes sense only if the liability you want to match coincides with maturity. Now, what if the maturity if 20 rather than 5 years? So when using the MATLAB, P1 equal to 21.4548, P2 equal to 17.8431, and the final answer is minus 0.1683. Okay, last example. Suppose that the stock price model follow the geometric Brownian motion ds t equal 0.1 st dt plus 0.2 st dwt with initial stop price s0 equal 30. At the initial time t equal to 0, write a MATLAB code using the Euler distribution with time step 1 per 400 to plot a patch of the stop price from time t equal to 0 to time t equal to. So when using the MATLAB, the result graph get the same on the slide.
Okay, my name is Shamil Arif and I will be talking about part B, which is the deterministic and Monte Carlo method. Monte Carlo method is a method named after the Monaco casino, which is that is a computational technique using random sampling for numerical solution. Valuable in addressing complex problems with inherent uncertainties, it provides a probabilistic approach where deterministic methods struggle. How it's used? It is used by employing random samples from probability distribution. The method estimates quantities or solves problems through statistical analysis. Its versatility spans various domains, offering a probabilistic edge where deterministic methods face challenges. Real-world application in finance. The Monte Carlo method originated in 1944, evolving from random number generation to a pivotal role in cost estimation and investment projection. By modeling uncertainties in factors like market fluctuation and project timelines, Monte Carlo simulation provide decision makers with insights into potential outcomes, enhancing the robustness of decision making in complex financial scenarios. The applications in finance are: in finance, Monte Carlo simulations shine in modeling and analyzing uncertain systems. They estimate option values, assess portfolio risk, optimize asset allocation, and stress test financial models. The method proved invaluable for managing uncertainty and dynamics in financial markets. So these are the steps for the Monte Carlo simulation. First of all is to establish mathematical model. Develop a mathematical equation representing the relationship between input and output variables serving as the simulation framework. Second is define input values. Choose appropriate probability distribution for input variables, capturing inherent uncertainties in the system being modeled. Next is create a sample dataset. Generate a substantial dataset with around 100,000 random samples, reflecting potential scenarios for comprehensive analysis. The fourth step is set up a simulation software. Configure Monte Carlo simulation software using input samples and the mathematical model. Consider variable computation times based on input complexity. And finally, analyze the result. Examine simulated result, understanding output distribution through statistical measures like mean, standard deviation, and variance. Facilitate informed decision making based on simulated scenarios. The following is an example of how to use a Monte Carlo simulation. The problem statement is: suppose you have an investment portfolio with an initial value of 100,000 US dollars. You want to project the range of possible portfolio values after 1 year, taking into account the uncertainties in annual return rates and market volatility. As you can see, these are the results. In conclusion, the Monte Carlo simulation reveals insights into the 1-year potential custom outcome for the investment portfolio, estimating a mean future value of $108,061.33. The central tendency serves as a point estimate considering the specified mean return rate and volatility. The $15,037.58 standard deviation indicates variability and risk, reflecting the influence of market fluctuations. The fifth percentile value of $83,613.31 suggests a conservative estimate, revealing a 5% chance of the portfolio falling below this level, while the optimistic 95th percentile value of $133,021.19 indicates a 5% chance of exceeding this threshold. In summary, the simulation provides a nuance and understanding of potential portfolio values, aiding investors in making informed decisions, managing risk, and aligning strategies with financial goals.